We're going to investigate how to find the electric field of a continuous charge segment. So here we have a line segment of uniform charge density with charge capital Q and length L, and we want to find the electric field at point P, which is some distance A from the end of the bar. Does the equation E equals KQ over R squared describe the electric field for this geometry? No, this equation is only useful when you're talking about a point charge. But we can use this equation and our understanding of superposition to help us find the electric field created by other geometries. This often involves calculus, but before we get into that, let's get a conceptual understanding of the process. Imagine that you model this bar of charge as a collection of smaller bits of charge. This red charge, let's call it Q1, is some distance from point P, R1. And because it's a positive charge, we can say that it would create an electric field pointing away from Q1 with a magnitude of E1. Now, E1, of course, would be K Q1 divided by R1 squared. Now let's look at this blue charge. This blue charge has a charge of Q2. It's some distance R2 away from the point, and it would contribute an electric field also going to the right with a magnitude of E2. And of course, E2 would just be K Q2 over R2 squared. And of course, we could continue to do this. So let's say this charge, this green charge, is Q3. Q3 is some distance R3 away from point P. And Q3 would also create an electric field going to the right with a magnitude of E3. And of course, E3 would be K Q3 over R3 squared. Now, if we continue to do that for all of these little bits of charge, we could approximate the field at point P by just summing up all of the electric fields. So the electric field at point P would just be E1 plus E2 plus E3, etc. To get a more accurate answer, though, our little bits of charge have to be much, much smaller. In fact, they need to be infinitesimally small. And just like Q1 created E1, any little tiny bit of charge is going to create a tiny electric field at point P. And if we summed up all of those tiny contributions, we could find the electric field. So what does that process of summing up tiny little bits remind you of? Integration. When we do these sorts of problems, you want to draw the situation, and on your drawing you should identify this tiny little sliver of charge that you're working with. So I'm going to pick this little sliver right here. And since this sliver has a tiny infinitesimally small bit of charge, I'm going to label that amount of charge as dq. Okay, so a tiny little bit of q. And we know that this sliver is some distance little r away from point P. Note that I was careful not to put this sliver at any special location, such as at the middle of the bar or at the ends, since those locations could possibly have you make inferences about the electric field that are unique to those particular locations. So we can see that this little dq is going to create a tiny electric field at point P, which I'm going to call dE. And we know it's going to point to the right because this little bit of charge is positive. Now, since we know that E equals KQ over R squared, we can say that this little bit of field caused by this little bit of charge is dE equals K dQ over R squared. Again, it's important to note that this R is the distance between the point and my sliver. So each sliver on the bar is going to have a different R value, and that little sliver is going to create another dE, and this little sliver is even closer, and it's going to create another dE. What we have to do is basically sum up all of these little dEs in order to find the electric field at point P. So to find the electric field at point P, we said all we have to do is sum, which is just the integral, all the little dE's. And of course, dE is just k dq over r squared, so I can plug that in. And this is k dq over r squared. Now, as we look at the electric fields created by all these little different slivers, is r changing or is r a constant? R changes, so we can't do this integral yet. We have our integral in terms of dq, but we know that we also need to account for the fact that r is changing. So in order for us to solve this integral, we need all of our variables to be in terms of a single variable. So how do we do that? Well, we have to look at these terms, dq and r. dq is a charge, r is a length. So how can we relate a charge and a length? With linear charge density. So linear charge density is lambda, and lambda just equals charge per length. So for this entire bar, it's Q divided by L, and since this bar is of uniform charge density, the ratio of charge per length for any section of the bar should be the same. So before we think too abstractly about linear charge density, I'm just going to give us a tangible example. So here we have a bar of charge 20 microcoulombs, and let's say the bar has a length of 4 meters. Okay, the linear charge density of this bar would just be Q over L, so that's 20 microcoulombs divided by 4 meters. So that would be 5 microcoulombs per meter. Now, if I were to cut that bar in half, okay, and I'm only looking at this blue section, then the linear charge density would be half the charge, 10 microcoulombs, half the length, 2 meters, and we'd still get the same linear charge density. Okay, it would still be 5 microcoulombs per meter. So if I were to ask you how much charge would this orange section have, so let's say this orange section is 3 meters long, okay, then how would you do that? Well, you know that the linear charge density is 5 microcoulombs per meter. This section is 3 meters long, so you kind of figured out the charge is 5 microcoulombs per meter times 3 meters long. Meters cancel out, and you would get 15 microcoulombs. So what you did here is you actually figured out that the charge on any section of the bar is just equal to lambda times the length of that section. So we're going to kind of keep that in our back pocket. I'm going to write it at the top. So the charge of a section of the bar is just lambda times the length of some section. Okay, that same section. All right, so let's get back down to solving this situation. So here we know that the linear charge density is capital Q over capital L, but we also know that this is the same for a tiny little bit of charge. So this would be the same for dq divided by the width of our sliver. So now we have to figure out what the width of our sliver would be. This little width or thickness of the sliver is along the line of r, and it's a little bit extra of r. So I can call this thickness dr. Now, if instead of having the thickness be along the line of r, for instance, let's say you had a situation where you had a bar and I wanted to know the electric field here at point P, and I wanted to look at this sliver. This would be r, but the thickness is not along r, so we can't call it dr. In fact, what we would do here is we would maybe call this distance y, and so we would call the thickness dy. So it's important to be careful about what you're naming these thicknesses to match your picture. So here we see that r is going from the point to the sliver, and dr is a little bit of that extra bit of r. So now let's go back to this lambda. So now I know that the thickness, okay, of my sliver is dr, and so I see that I could rewrite this equation as dq equals lambda dr. Now this is actually no different than what you did up here. Right here you saw that the charge was equal to lambda times the length of the section that you're interested in. So that's the same thing here. the charge of this little sliver is equal to lambda times the length of this little sliver, or the thickness, this dr. So the whole point of doing this was to get r and dq in terms of the same variable. So now we've done that. We can now substitute in, for dq, we can substitute in lambda dr. And now you can see here that all of our variables match. K is a constant, lambda is a constant, and you have dr and r squared. So we're golden. Now we want to look at the limits of integration. Your limits of integration are determined by the integration variable. So for our case, what is that integration variable? It's r, right? We're taking this integral with respect to r. So what does r mean? The physical meaning of r? Well, it's the distance between the slivers and the point. So all we have to do is say, all right, well, what's the smallest r value? Well, that's when the sliver's here, right? So that's the smallest r value. And what's the longest r value? Well, that's when the sliver's down here. So our limits of integration would be from when r equals a to when r equals a plus l. Now that is basically the physics of setting up this equation. At this point, we're just going to be doing math. So I can go ahead and pull out the k and the lambda, because those are constants. And I have the integration from a to a plus l of 1 over r squared dr. And I can write that as r to the minus 2 dr. And so if I integrate that, I get k lambda r to the minus 1 divided by minus 1. And I'm going to evaluate that from a to a plus l. Okay, so now we have a little bit more space, and this is exactly where we left off. So I can take this minus 1, put it up front, and this is minus k lambda. And r to the minus 1 is the same thing as saying divided by r. And this is again from a to a plus l. So this is just minus k lambda times 1 over r. And we want to evaluate that from a to a plus l. So that would be minus k lambda times 1 over a plus l minus 1 over a. I'm going to distribute this negative sign out. So this now becomes k lambda minus 1 over a plus l plus 1 over a, which is k lambda 1 over a minus 1 over a plus l. So now we just need to find a lowest common denominator, which would be a times a plus l. So here I'd have a times a plus l, and that would mean I would need to multiply the top here by a plus l, and I would subtract, same thing over here, a times a plus l, and I'll have to multiply this numerator by a. So after all that algebra, we get k lambda times a plus l minus a over a times a plus l, which of course would be k lambda, and then you have a minus a, those go away, so it'd be k lambda l over a times a plus l would be the electric field at point P. Now lambda is a term that we gave this problem, right? We weren't given lambda at the beginning, so we can't have an answer in terms of lambda. But we already decided that lambda was capital Q over capital L, which was given to us. So we can go ahead and put that in for lambda. So it's K capital Q over capital L times L over A times A plus L. And one of our L's cancels out. So here we have KQ times 1 divided by A times A plus L would be the electric field at point P. And of course, we saw that all of those individual fields were pointing to the right. So this would also sum up to be an electric field to the right. So we'll put that here, to the right. And we have solved this problem. But there's one more thing I want to show you, and that's thinking about the limiting cases. So imagine that instead of just being a little distance a away, imagine you're really, really far away, where a is much, much bigger than the length of the bar. Now, I'm not talking about infinitely far away, I'm just talking about where a is much bigger than L. So in that case, this extended bar no longer really looks like a bar. If you go far enough away, that bar is going to look narrower and narrower to you. So this bar is going to kind of look like a point charge. So let's see what happens if we look at the limiting case. So we know that E is KQ times 1 over A times A plus L. Now, if A is much, much, much greater than L, A plus L basically just becomes A. So then you would have KQ over 1 times A, which is A squared, which is the electric field for a point charge. So when you look at this thing from a long distance away, it sure does look like a point charge, which is exactly what we would expect.